So it seems there's fewer people here today than there was on Wednesday. Why is that? Anyway, so how was it? All right, I'm not hearing a round of applause. A little harder? Okay. All right, thank you. What's your name? Yeah, we can announce it to the class so they can all thank you personally. Anyway, it was too long or just, it was not so different. Was it too long? Okay, so the final should be twice as long? Okay, so it's being discussed in the discussion sections. Okay, so now you're calibrated. You know what to expect next time. Anyway, speaking of next time, we better have some content. So okay, let's pick up kind of where we left off. And, remember, just to refresh our memory, because we've been thinking about other things. We had this engine, and it was the Carnot cycle. And we had this picture we could draw. Right, we went around this kind of iconic cycle I'll draw in there. That's that thing we did. We worked out all the details. I'm not going to do that again. And we saw that, a measure, this is kind of interesting. Okay, so the efficiency, a reasonable definition is like the ratio of the work we got out to the cost. Making that Q sub H took some effort. We had to stoke a steam engine or something. So, everything has a units of energy, right? The work and the heat, they both are measured in joules or whatever your favorite unit is. The ratio is dimensionless, right? And for the Carnot cycle, we found that was nR T hot minus T cold log, and the first step, from A to B was an expansion. There was a ratio of volumes bigger than 1, right? So now we're looking at all the positive quantities. The signs, always beware of the signs. But the way I draw that's the positive work we're getting out of this thing. There it is in the numerator. And in the denominator, we got sort of a very similar looking expression, but it just had the T sub H. And, you can refresh your memory looking at the book or the notes about it. And if I work that, let's call that eta. That's a Greek. For those of you who are not in the Greek system, that's an eta. And everybody seems to always use it for efficiency. If I do the algebra, everything cancels except the temperature factor, and I get 1 minus Tc over Th. And that's the efficiency. And we can see a couple things immediately. If I don't have any temperature difference, right, eta equals 0 if Th equals Tc. Right? You can't get something for nothing, and you need to have a gradient of temperature to get anything out of it. And if you have a gradient of temperature, then you can get something out. And the bigger that gradient is, the more you can get out. And you see this everywhere. If you have, probably some of you have been to Vegas, right? Which is not my favorite place. It's okay. I've had arguments. I had a Chem student. This was quite a few years ago. Very interesting guy. He introduces himself to me by saying, "I have the lowest GPA at UCI." And I thought, I don't think so. Okay, but it was pretty low. And he was going to go to Vegas. He was a biker. He had a shaved head and a beard. jeans jacket with no sleeves, chains everywhere. He rode a bike. And he was going to go to Vegas, so we would have these interesting discussions after every class. So he was a loyal follower. And he was going to Vegas, and we had a discussion about probability, very much related to S equals K log W. But he was convinced that if you let's say you were flipping coins in Vegas, you don't do that, but if you flipped 9 heads in a row, and you're going to flip it one more time, what's the probability of getting a heads? What do you think? He was convinced otherwise, like the forces of nature were not going to let it happen. Anyway, so yes, but if you go to Vegas and you get sick of that, you can go to the Boulder Dam, right? There's this big dam, there's water behind the dam. And if there's water behind the dam, then you have a gradient. It's not temperature, but it's potential energy, right? You have some water at a higher potential energy than another, and you can get something out of it, right? And all those power lines that you see crossing the desert heading towards Los Angeles is testament to that fact. So if you have a gradient, a system that's out of equilibrium, then you can get something out of it. And this example here is just one example, ideal gas, what is the relevance. But this is a quite general result. I mean, this is for temperature, and I presume there are other things, like if you had a dam, there would be something. And so this is like the theoretical limit of how efficient that can be. And it's the second law is what is the final arbiter of this. And so if you were to propose something that would exceed that efficiency, and you're writing a patent or something like this, and you propose to exceed that, then it would be impossible because it violates the second law. So I had a question on an exam once in thermodynamics, which I'll tell to you now because it's sort of related. Now, it wasn't in the undergraduate class, so don't worry. I'm not going to ask you this. But the question went something like this. You had decided to drop out of graduate school and do something more intelligent with your life, so you went to law school. And now you're sitting in your office looking through a BMW catalog. By the way, students don't like questions like this on exams because they have to read too much, and it's not funny on an exam, is it? But anyway, you're looking at your catalog to get your next BMW, and a patent comes across your desk, okay? And it was for something called an inverse jouleometer, which I made up, which is a device that has a propeller on it, okay? And you stick the propeller in your, it's a ratcheted propeller, so it can turn one way and not the other. You stick that in your beer, okay, at room temperature, and the random motion of the beer turns that propeller one direction and not the other, and it charges a battery. And the energy of the beer, the energy that goes into the battery, it comes out of the thermal motion of the beer, right? Because after all, the molecules are bashing around. So the beer cools down, which is, for some people, a desirable thing. And you charge your iPhone, which for everybody is a desirable thing, right? So you had to explain which laws of thermodynamics this obeyed and which ones they violated. So did it violate all laws of thermodynamics? No, the first law is fine, so the energy was conserved, but the second law, right? So you can't take something that's at room temperature and take heat out of it, and do something. Okay, anyway, this is an interesting topic. Engineers, of course, spend a lot of time talking about it, but that's enough for this. Let's move on. And this is just something I'm going to mention in passing. There's something called the Clausius inequality. Let's use the eraser. So Clausius, let's not have a history lesson, but he's one of the OG thermodynamics people. He had a very impressive beard. You know, I always get beard envy when I see these old pictures of these people, right? And I have a T-shirt with this picture and an equation which I will derive on it. I would have worn the T-shirt today, but you know, you for some reason you leave a T-shirt in your drawer for a few years and it shrinks by itself, right? So anyway, let's derive this. So we have this. This was in a sense our definition at the beginning of entropy, like a little change in the, like if we have a system, right, and we do something to the system, and we do it reversibly, and some heat goes into the system, or comes out, then there'll be a little change in the entropy, and it's ds equals dq reversible over t. And this equation is y. For an 80, I'm saying words you want to forget about since Monday, right? But if I do an adiabatic compression and I do it reversibly, there's no heat, right? So dq reversible is 0, and so the delta S, the ds of that gas, is 0. Now, if I do it irreversibly, it's not 0. And if I do a reversible compression of isothermal gas, right, and a little bit of, so I'm doing work on it, right? I'm compressing it. Its energy it wants to go up, but it can't because it's isothermal. And I do a little bit of compression and a little bit of heat goes out. Then the gas's entropy goes down a little bit, because remember, when I compress it by, if the volume goes to half as much as of the initial, and the temperature doesn't change, I got that minus R log 2 result for the temperature change. But now in general, and so we're gonna get away from the reversible, and we've already done that. We know this is true. This is the second law acting here, right? So second law, this is a consequence of that. ds is always going to be bigger than that, and if I do it irreversibly, right, then it's going to have to be that way. So if I have an isolated system, and this is a little bit of review, and I could have asked, I don't think I asked this, did I? But I could have said, what is an isolate, on that first page? Isolated system. And if I didn't ask it then, maybe I'll ask it later. So what is an isolated system? Yeah, nothing. Nothing gets in. Nothing gets in or out. There's no work done. Adiabatic, you can do work. Isolated, it's just a box, and it's like the universe is like the universe you could think of as a rather large isolated system, because there ain't no other universes unless you take quantum mechanics. Then you start talking about these things. But an isolated system, then ds is going to be greater than or equal to 0 because dq is 0. But that, still something could happen in the box, right? I mean, I could, you write stuff, life goes on inside the box, and the entropy's going up, and the box is isolated. But now, just to remind you of that, S is a state function. And so that means if I go around a loop, and we use this with the Carnot cycle, right? If I do this, if I go from A on a road trip, oops. You're probably thinking, I want to go on a road trip and just get out of Irvine for a while. It's a good idea, by the way. And then come back to A, right? I've gone around in a loop, and delta everything is 0, right? Delta S equals 0, delta U equals 0 for a closed cycle here. And we can write that mathematically, and people don't often like this, but that integral with a little circle on it, you've encountered that, I assume, in a math class, and that's like a line integral. Like if you're going to integrate the the dot product of some vector, like a vector potential with a little element of distance and go around a circle in some E&M class, you'd write it like that. And that integral around a circle is equal to 0, okay, because it's a state function. And so what I can do, because my ds is greater than or equal to dq over t, I can do this, right? I can say the integral of that around a circle is greater than or equal to the integral of dq over t. That's a q. Let me make sure I can read my own handwriting. I'm just doing algebra here, but this is equal to 0. So we get the Clausius inequality. This is not the Clausius-Clapeyron equation, which is the one that Professor Shaka told me that he had actually met someone who didn't know what it was once, and he was upset by that. Same dude, right? But it's a different equation. So he may, if you're taking Chem 5, he may ask you this, because he knows what's going on in here. And the Clausius inequality is this. And so what that means is if I go around a cycle and I look at the heat, and the temperature can be changing. I go around a cycle and heat's coming in, heat's going out, at all the steps. If I weight that dq around that cycle by a t, then I'm going to get something that's less than or equal to 0. Okay. All right. So this, that's just one of the sites along the road trip through thermodynamics. It's an important thing, but in here probably we'll just mention it in passing. We're making progress though on this road trip because we're now into topic 3, okay? And I think they call it something like calculating entropy changes. And we did a bunch of this already, okay? So we don't have to spend too much time seeing this site. Let's see. We have our kind of defining expression, and we can calculate. I'm just sort of again sort of reviewing, just putting these down so we have them here. Oops. If we want a delta S, and if we have an initial state and a final state, I can go from and so I'm not necessarily integrating over t, but if I had dq equals c dt, then that would be an integral over temperature. But it could be some other variables. I'm not. We have to turn the integral into something that we're actually going to do, right? Use it, So there's the practical matter of doing the integral, but the thing is written as an integral without like choosing our variables. So I'm just writing initial and final. And as we've seen, let's talk about let's look at again one more time at the reversible versus irreversible compression. And we'll have this T equals T naught equals a constant. So this is the isothermal. The isothermal case. And we'll just look at how this expression and how that Clausius one kind of works. And so recall, we had, let's say, probably monoatomic, but we did work, right? So V naught goes to V naught over 2, right? But that, for example, but I'm just going to leave it in general, right? We don't always have to to have that particular example. If it's a compression, the final is less than the initial, right? And then the argument of the log is less than 1. And so the work is positive, right? Compressing, we do positive work. If the gas is expanding, the gas does the work, and we do negative work on the gas, and then that V final being bigger than V initial for expansion, the log of that is positive, and so the minus sign outside determines the overall sign. We had heat, which is going to be plus, nRT log V final over V initial, because remember, delta U, Q plus W, and that's equal to 0 for this isothermal. We have this expression we got for the entropy, and there was a formula for it. We had something like, let's write it down. Write it over here in our marginalia. S is S naught plus NR log T over T naught, and I could put that little C there if I wanted to have a diatomic, but C equals 3 halves for the mono, that the fraction without any R's or anything. The exponent has to be a dimensionless number, just like so I think I talked about how you always want to have dimensionless things, so it's 3 halves, not 3 halves R or something like that. So if I use that for this case, then I get my NR log V final over V initial. And so this is reversible, and so this is Q reversible, right? And my delta S is indeed Q reversible over T, right? And I'll make these all knots here because we have our T equals T naught, right? So that formula worked here, but we didn't necessarily need to use that. We have this expression that we derived, and it was on your exam, even though you really didn't absolutely need to use it, but it was there. Q of the surroundings, is equal to minus Q. Right? I'm going to write this Q over T naught because I'm not calling it Q reversible. It's just Q for this problem. This is the first law again, and delta S of the surroundings is minus Q over T naught, and so delta S of the universe is equal to 0, right? So that's consistent with it being reversible. So if I do an irreversible, so let's say we let's draw like this picture. This was initial and this was final. So I'm thinking now of an expansion. You got to pick one. And so we did this work. So work was less than 0 for an expansion. Q was greater than 0. Q surroundings was less than 0. Delta S was greater than 0. Delta S of the surroundings was less than 0. Right, and we did this problem. For the I'm going to swing up here. For the irreversible, draw the same picture. But we'll do it with P external like that, and that's my work, right? So delta S is the same as above, which was NR log V final over V initial, right? That was the state function, T equals T naught. We go from here to here. The same as for this example. But the work is still less than 0, but it's smaller in magnitude, right? And so Q is greater than 0, but since it's smaller in magnitude, and the reason I'm the reason I'm saying that it's smaller in magnitude is because the area here, right? This area here is the entire area under that curve, and of course, this one, it's that rectangle, right? So the gas didn't have to expend as much effort to push that volume back out to push it to the bigger final value, and didn't do so much work. The Q of the surroundings was less than 0, but smaller in magnitude. Magnitude means, minus 1 is smaller in magnitude than -2, right? But -1 is actually bigger than -2. You have to be careful, like on an absolute scale. Just the size of the effect is smaller in magnitude here. And so delta S of the surroundings is less than 0, but smaller in magnitude. So what that means is, and this is sort of the punchline of this comparison here. Now, we've talked about this already, but we're talking about it one more time. Then I promise I won't talk about it for a while. But we're going through this calculation yet again to show, delta S goes up that much, right? And delta S goes down that much. The surroundings goes down that much. So there's two possibilities, right? This is the reversible. Because the system had to do all that work when it expanded, and that took a lot of heat coming out of the surroundings to make up for it, to keep the delta U not changing. And so the gas's entropy went up, but the surroundings went down by that much, by the same amount, but same magnitude but different sign, so they exactly cancel. But for the irreversible one, here's the delta S of the surroundings. I hope the picture being worth 1,000 words, and I don't know how equations factor into this value calculation, but it just doesn't go down as much, right? And that's why this one had delta S of the universe equals 0. And if you put those together, it's greater than 0 for the irreversible one. Okay, so that is like one more time talking about the difference between reversibility and irreversibility. Okay. Yeah, I hope that makes sense. So, okay, we're going to talk about now something a little bit different. So no more gases expanding for a few minutes. The world is more than just gas, although, if you watch politicians talk, you might get a different opinion. So we're talking about phase transitions, right? Phase transitions, we all know what they are. There's the ones solid, like a block of ice melting, your ice cream melting, I don't know. Solid into liquid, right? Melting. Sometimes they call this fusion, and the thermodynamicists call it that for some reason. You could have a liquid to a gas, boiling, a vaporization, whatever you want to call it. But we can have others too that maybe you wouldn't think of. Like we can have a folded protein going to an unfolded protein. Or all kinds of stuff like that, right? So biological liquid crystal phases changing, when you change some parameter. That's an example. Or we could have something that's magnetized. And we can unmagnetize that. So I like to listen to podcasts sometimes, and there's one I like about people who repair electric guitars, because I like to do that myself. And someone had an electric guitar which has little magnets in the pickups. The strings vibrate, the metal strings vibrate, and there's a magnet below the string, and as that thing vibrates, there's a magnetic field that changes in time, and there's a big coil of wire around this. And you all know from your physics class, if I have a changing magnetic field in a coil, it induces a current. And that current is very weak, but goes into this big thing called a Marshall stack, and it damages your hearing at the end of the day. Okay, so it's very much amplified. Now, this guy, he left his guitar. He was in a helicopter, and he left it near the engine, and there's a lot of some big, large magnetic fields there, and it has somehow demagnetized his pickups. So all the spins that were all pointing in the same direction, the atoms, the magnetic moments of the electrons and they're all aligned. If they get randomized, then there's no macroscopic magnetic dipole anymore. That's a phase transition too. And so that's what we're talking about. But let me draw a useful picture. And we'll come back to this. And I don't think this picture's in your book. But we're going to take Q and we're going to take T. And we're going to add heat to something, okay? And we're going to watch what the temperature does. And so I'll put a couple lines to guide the eye here. And it's going to be water at 1 atmosphere. Okay, I'm not going to use any kind of kilopascals or bars, anything like that. And I'm going to put a line at 0 Celsius and at 100 Celsius. Oops. So if I have water at 1 atmosphere and I'm below 0, what is it? Ice. If I'm between 0 and 100, what is it? And if I'm above 100, what is it? Right, okay. So if I start with it pretty cold and I add heat, right? And remember, like dQ is C dt, and this is the heat capacity. So if I want to be fancy, I'd look up the heat capacity of ice, and I would draw an accurate picture. But okay, if I'm below 0 and I add heat to this piece of ice, this temperature goes up, right? So it goes up and up and up, and so it hits that point, and then what happens? And it's flat, exactly. So it goes flat for a while. And what's happening when it's flat? Like, So I have a, I've got my highball glass waiting for the good stuff to go in, but I'm too busy lecturing. So heat is going in from the surroundings, and it starts melting, right? So I've got some liquid in contact with the ice, and assuming it's being stirred or something, they're both at that same temperature. That's why we put ice in our drink. We want the drink to be the same temperature as the ice. And so when I add a little bit of heat, I don't raise the temperature. What do? I convert some ice into water, and sort of, if I add one, microjoule, I'll do that to a certain amount. I add another microjoule, the same amount, right? So I'm sort of converting as I add heat, one phase to the other. When it's all gone, then what happens? I mean, then I just have water left. Well, it keeps going up in temperature until it hits this thing. Now I have water at 100 degrees, and then when I add heat, it boils. Then it keeps going like that. So I've got this sort of it's a continuous but not always differentiable function because of there's bends in it, right? There are these kinks in it. And that's a hallmark, in fact. I mean, if you become theoretical physicists studying phase transitions, it's the non-analyticity of mathematical functions, which is a term from complex variable theory, which is a hallmark of how these functions behave. But I've just got some kinks here. Now, this amount here, and this is an amount of Q, and this is an amount of Q. And you know this from even high school. You did problems like this, right? This we could call this. This is like delta H sub FUS. So delta H of fusion. And let's say I have, if I had 1 mole, I'm not going to assume like this is 1 mole. Let's say this is the heat of fusion. So that if there was 1 mole of water, that would be the number of joules it would take to convert 1 mole of water, 1 mole of ice to solid to a liquid at that temperature, right? And this one here, delta H of vaporization. And people will call it heat of vaporization. This is kind of almost a language convention. It's sort of a nickname. People throw that around. It's an enthalpy. It's the enthalpy of whatever vaporization. People call it the heat of vaporization, and implicit in that is the fact that we're at 1 atmosphere, and this is why chemists they like enthalpy and they like Gibbs free energy, because it's not the volume that's being conserved in this problem. You could do the whole thing at a constant volume. You could have a vacuum and throw a block of ice in it, and then it would melt, and you would always have a little bit of vapor, a little bit of water, and a little bit of ice in there in different proportions. Then wouldn't be H. It would be energies and things like that, Helmholtz free energies and things like that. But here we have the enthalpy being called a heat because it's the constant pressure heat capacity is what we're using here, because the pressure is constant, and so baked into this one. I mean, from going from a solid to a liquid, not much volume change. But if I take the liquid and I convert it into a gas, now we have an interesting problem we can do in the future, right? Because what happens to the volume? What is 1 mole of water's volume, and what is 1 mole of gas's volume at 1 atmosphere pressure? The gas has a much bigger volume, and so baked into the amount of heat I had to put in here was what? what physical process occurred when that phase transition occurred, going from liquid to a vapor. Yeah, there's work done, right? So if I boil that water, the water says to the room, "Hey, get out of the way. I'm gonna join you." Okay, and so you could imagine doing that process by some other, in thermodynamics, you always think about different paths, right? So you can think about a path whereby you go into the room and you create a vacuum, like you expand a balloon of some kind, so that you have a volume that's waiting for 1 mole of that water vapor, and then you make that, and then you put it in that volume. So even though, like when your teapot is boiling on the stove, you put water in, but then the vapor's coming out of the thing when it's whistling. Mine never seems to whistle, right? But they're supposed to whistle, and they're whistling and putting vapor into the room. They're doing work to make room for that vapor. Okay, so that's baked in to the energetics of the problem. And so we could go further. So really, when I'm water is an anomalous. We'll talk about this later, but as long as we're here and we don't have too much time left, water is an anomalous thing, isn't it? Right? What's different about water than other things that can melt and boil? Anybody know? Yes. Solid ice floats on liquid water. Yes. Normally, think about a bunch of marbles. Okay, do people know what marbles are these days? So these little round glass balls that back when childhood was not going to Kumon math on the weekends, right? You know what I'm talking about, don't you? Okay, try to get into the right preschool. You would play with these things. There was this thing called play, okay? And so let's say we had a bunch of marbles of all the same size. You'd imagine putting them in a jar, and they'd pack in there. There'd be like a hexagonal close packed, this crystal structure. The way they would arrange themselves in an orderly array. They just sort of, if they're all the same size, even if they're not quite, they come with a regular array. Now, if I made a liquid out of it, I'd kind of shake it up, and maybe it would be in a vibrating, like if your car needs a tune-up in your car when you're driving, now they're in a liquid phase. And the volume of that liquid phase would be a little bit more than the volume of that packed phase. That's a normal material. So if I had a block of ice, it should have a higher density. It should have a smaller volume. And if I have a liquid and I put something in a solid object with a higher density of the liquid, and there's gravity, right? We're not up on the International Space Station. What happens to the thing with the higher density? It sinks, okay? But water is different because when you freeze it, it makes this more spatially, it makes this tetrahedral structure, which instead of the water molecule all kind of, it's like some sort of, you see these at UCI, these dance teams, right, or something. Instead of just being sort of packed together, standing in a sort of a disordered way, they all have to stand and hold hands in a certain way, and that's a lower density. So ice floats. Is this important, do you think? What if ice sank? What if you were a fish, and it was wintertime up in Minnesota, and the lake froze? What would happen to you? I shudder to think about it, right? So like the fact that water has these anomalous properties is very important for life, I think. But okay, so we can calculate a few things from this. Why was I talking about that? Oh, so when we go from like the, let me turn on my light here. We're going from the solid to the liquid, or from the liquid to the gas. There's two things that are going on, right? The molecules are interacting with each other. There's potential energy, right? So there's hydrogen, like the hydrogen bonds of the ice are being broken, but then the hydrogen bonds of the liquid are being formed, and they're not all that different. If I have the hydrogen bonds of the liquid going to the vapor, then I'm breaking putting some energy in to break some bonds. I'm putting some energy in to do some work. But for this one, it's mainly just entropy that's really changing, isn't it? So I can calculate that, like the delta S of the fusion would be this delta H of the fusion divided by the melting point. So I'm using melting and fusion. This is the melting point. And I can calculate the delta S of the vaporization as being that delta H of vaporization divided by the boiling point. When this one's 273, K is 0 degrees Celsius. And this is what, 373 K? 100 degrees Celsius. Yeah. Okay. So, and we'll do some problems like this. I have to cook some up. I'll say one more thing. We can finish one more thing. How long have we spent talking about the second law of thermodynamics? A lot, right? So we've run out of time, so we have to talk about the third law in 60 seconds or less. Because there is a third law of thermodynamics. And this one is, S is equal to 0, and I'll put usually at T equals 0, okay? And so unlike energy, energy, you're always free to add a zero of energy. Like you can always say, oh, I insist on including MC squared, for everything, right? Because you never know when you're going to be making an atomic bomb out of it. But you see what I'm saying? There's always a sort of an ill-defined zero of energy, but not with entropy. So, and this is we can relate this to this idea: S equals K log W. Remember, W is equal to the ways of arranging things, and so when I have a finite temperature, then I have a little bit of a mojo. Okay, so I have a little bit of, like, if in this room, if I had enough coffee, I have a lot of seats available to me, because I have the energy to walk up there and sit anywhere I want. There's a lot of seats, right? But if I'm really lazy, the only place I'm going to sit is in that chair. So there's only one place for me, okay? And when W equals 1, then S is equal to 0. So if I have a let's be a little bit more scientific about it. If I have a system with a bunch of quantum states in it, right, and there's so little thermal energy that I am stuck in the ground state, then there's only one state available. But I wrote usually because you can have degenerate ground states in some systems. Like an example, like you know about degeneracy because you did take. What is degeneracy? I mean, I know about the other kind, okay, but I will not. I'll say no further. But about in this class, degeneracy means. How many levels are there with the same energy? Right. So like hydrogen atom, 1s, 2s, 2p.